Black holes, phenomena of great interest to physicists, and for good reason. Predicted 200 years ago and overgrown with a solid theory over the past 100 years, until relatively recently, they spoiled us only with pieces of evidence of their existence. Only 5 years ago, it was possible to obtain a photograph, if it can be called a photograph, of a black hole. With extensive theory and research on black hole radiation, we are still unable to answer one of the most fundamental questions about information itself. The methods used to describe black holes give rise to consequences that run counter to our understanding. To make more sense of this issue, let us take a moment to consider the aspects involved. Beware, the formal part begins.
Let's start by looking at black holes. What do we know about them? According to our understanding of black holes, they are characterized only by their mass, charge, and spin. The remaining characteristics of the radius, surface area, entropy, etc. follow from those listed. It should be noted that black holes do not last forever. They evaporate in a process called Hawking radiation. This is a process during which a particle-antiparticle pair appears near a black hole, of which the first manages to fly away into the vastness of space, and the second is destined to fall into the black hole, which, being an antiparticle, will reduce the mass of the black hole. This process will play its role later when we try to use it to resolve the most curious paradox, the essence of which everyone has already guessed. Let's move on to something more interesting. Quantum theory implies the conservation of information, but how do we understand this? In a closed system, the information about it is preserved under the evolution of the system. Let's imagine the people talking in a closed room with walls that perfectly reflect sound. At some point in the conversation, we didn't hear what our partner said, but we don't want to ask them again. If we manage to track all the air particles, we can reconstruct their movement from the moment when that very word was uttered, and by analyzing their kinematics, obtain information that would seem to be lost forever. According to this belief, considering a black hole and some object falling into it as a closed system, we could, in the black hole, observe the object, retain information about what fell into it, and for this we would have enough characteristics of the black hole, but presumably this happens with some information, such as mass and charge.
The black hole information paradox centers in a conflict between quantum mechanics and the principles governing black holes. According to quantum mechanics, information within a closed system cannot be destroyed. However, when a black hole emits Hawking radiation, it violates this principle. Information disappearance in a black hole occurs if it truly obeys the thermodynamic description proposed by Stephen Hawking. However, this phenomenon is incompatible with the general principles of quantum mechanics and therefore represents the most serious problem facing quantum gravity.
In order to resolve the paradox, wildly different solutions have been developed. Some of them claim to solve the paradox, while others give some insight towards the solution. Many of them are still under investigation, since the search for a solution has appeared to be difficult. By trying to solve the information paradox, one might have to deal with energies at the Planck scale. Here, the known laws of physics seem to fall apart. In order to fully describe the black hole in a physical way, we might need a new theory of quantum gravity. Also, for a solution for the information paradox, quantum gravity has to agree on both quantum mechanics and general relativity. Since Hawking found out black holes radiate, a lot of research has been done in order to find and define such a theory. Here, we take a look at some famous proposed solutions involving the information paradox. Common sense suggests that to resolve this paradox, we should check whether or not information is being carried away from the black hole unaccounted. The first place to look for this lost information is in the Hawking radiation itself. If somehow information was carried away in the Hawking radiation in a way that was unaccounted for in Hawking's original derivations, maybe the paradox could be resolved. First, one may take Hawking's theories to higher orders, as Hawking's original derivation was in fact only to the leading order, but accounting for higher order effects only allows for an infinitesimal increase in information carried away by Hawking radiation. This can never account for the information loss going from pure to mixed states, so it seems like new physical formulations will be needed if the information is to be carried away with the radiation. One way to overcome the above violations is to consider that the semi-classical theory of gravity, an approximation of quantum gravity from which Hawking radiation is formulated, fails for Planck-sized remnants. This is true because of the size of the remnant. Due to its small size, it can be considered as a particle, and quantum processes, such as quantum fluctuations, can have drastic implications on particles. And as we do not have a comprehensive theory of quantum gravity, we cannot exactly predict what happens to a Planck-sized remnant. But we can consider a possibility in which quantum processes terminate Hawking radiation and give rise to stable Planck-sized remnants in which information is conserved. This solution does not violate the Bekenstein bound or causality, but has one major obstacle. In order to conserve an arbitrarily large amount of information, due to their relatively small size, Planck-sized remnants must possess an infinite number of internal states. One suggestion to overcome this problem is that a large black hole can leave behind an infinite number of these remnants, so that each one has a finite number of states. Another possibility is that, as the entropy of a black hole, called the Bekenstein-Hawking entropy, depends on the size of the event horizon, the surface area, and increases with the increase in the surface area, given by the Bekenstein-Hawking formula, we can say that instead of a stable Planck-sized remnant, we have a large remnant whose surface area increases with the increase in entropy and consequentially with the increase in information. This solution does not require infinite internal states, but has one major problem. In order for a large stable remnant to be greater than Planck size, it needs to violate the semi-classical theory of gravity, specifically Hawking radiation, to not radiate energy, as it predicts that black holes must radiate energy in the form of Hawking radiation.
Having considered everything previously said, there is a feeling that the paradox remains unresolved. It is true that none of the solutions free from contradictions, and many demonstrate our lack of knowledge. However, they all have a chance to be improved in the future to provide a comprehensive solution to the paradox. Perhaps new discoveries will offer fundamentally new approaches, or it is possible that this paradox will forever remain unresolved for humanity. What is certain is that we will not stop looking for solutions where our understanding is challenged, as in the current example of black holes.